seem to be perfect. But now we've got all kinds of data, so of course the wheels start to come off at least a little bit. But here is the past 420,000 years. This is a time of Earth history for which we have just exquisite records recovered from the Antarctic ice cores. And so we know how much carbon dioxide was in the atmosphere. You literally have gas bubbles preserved that you can analyze and tell how much CO2 was there. From the hydrogen isotopes in the ice, we have the temperature, and any knucklehead can see that the temperature is varying with the CO2. That's impressive. Methane varies as well. That's this line. And make sure I'm not telling a story here. These are variations in oxygen isotopes in, I thought it was shells, but I can't read the subscript. It looks like it's saying atmosphere. Anyway, here's the insulation. And this is the Milankovitch energy cycle, computed not with paper and pencil now, but far more precisely. And the correlation is still there. You can correlate ice ages with various features in the record. But as you can see, it wobbles. It's not as strong a correlation as it was. And it has to be said that the full story linking orbital variations and climate variations and the mechanisms that modulate it and make it vary, it's not perfectly understood by a long shot. But the variations are there, and there's no question that CO2 and temperature in particular have been tightly linked. CO2 is a really key point. It's a component of the atmosphere, and it relates both to a biological carbon cycle, where we've got plants turning CO2 into organic material, biomass, and we've got animals and other things turning organic material back into CO2. Photosynthesis and respiration. That's the biological carbon cycle. There's also a geological carbon cycle where carbon gets buried in sediments at the bottom of the ocean. Those sediments eventually find their way up on the continents where they're eroded, and carbon gets pulled back into the atmosphere by these processes of erosion and volcanism and metamorphism. So this pathway of carbon flow from organic material back into the atmosphere transports, remember high school chemistry? Moles of carbon. It transports 7 times 10 to the 12th moles of carbon per year. And that's been going on at about that rate for billions of years, as Carl Sagan would say. Now, of course, we're doing something else. We're drilling down or digging down and removing organic carbon as fossil fuels, and we're burning it. So we're putting it right back into the atmosphere as mobile CO2. The question is, how does the rate at which we're doing that compare to the rate at which nature was doing it anyway? Well, of course, it's been increasing. Since about 1850, Industrial Revolution, huge amounts more. In fact, appallingly large amounts. The amount of carbon that we dig up and burn, these are the numbers from 2013, a United Nations report, more than 300 times more than would be recirculated just by nature alone. It's a huge effect. a great perturbation of the natural cycle. And it's caused, this is another one of these iconic figures. This is Dave Keeling's record of CO2 measurements at Mauna Loa, where in 1960, it was about 315 parts per million CO2, and now it's 400 parts per million CO2. On a scale versus, here's the past 1,000 years, CO2 measurements from the ice cores hovering right around 280 parts per million, the so-called pre-industrial level. And now, this is what we're doing. We've added hugely. This is the so-called hockey stick graph, in which the CO2 goes way up sharply at the end. And it was the data supporting this that was being refined and argued about by Michael Mann and others about 10 years ago, when their emails regarding exactly how to present it were grossly misinterpreted and led to all kinds of claims that the data were being cooked. And nothing could have been less true. So this is from a very recent paper by a whole lot of climate scientists. First author is a guy named Jim Hansen, an Iowan who was for many years director of the Goddard Space Science Institute in New York City. And it's again a time axis. Here's 1850 up to 2000. And here, on a different time scale, is thousands of years. So here's 400,000 years before 1850. And these are these glacial cycles that you saw on an earlier graph. And what's represented is so-called greenhouse gas forcing, the amount of energy being retained in the atmosphere by the effects of these greenhouse gases. And this is the so-called Vostok temperature, the ice temperature recorded by the ice core, the variations in the ice core. And if you can make them just absolutely congruent by multiplying the variations in temperature by 0.5. 0.5 is just to make it show how close the correlation is. Working forward from 1850, this line represents the forcing being added, the energy being added to the atmosphere by greenhouse gases, which means mostly CO2, also methane and nitrous oxide. And you can see that the forcing due to the greenhouse gases has risen steeply. Compare it to global temperature, which has risen not quite so much. And the reason, well, one reason for that is that the total forcing happens to have been cut way down by all kinds of particulates being put into the atmosphere as well, and especially by various volcanic eruptions, which have put lots of particulates into the atmosphere and modulated the total forcing. Although recently, the total forcing is now really beginning to approach the greenhouse gas forcing, and sure enough, temperature is rising as well. So this effect is definitely occurring. And the fact that the temperature is not following the greenhouse forcing or the total forcing as well as we might expect has to indicate that a lot of the energy has gone not into temperature, but into climate change. And we see that most recently, of course, locally, in the drought. And I'm afraid we might also see it in this year's El Nino, which was predicted to be, you know, this super El Nino that would get us huge amounts of moisture. This is from the Chronicle at the end of March, and it shows how the precipitation actually received at points ranging from Seattle down to San Diego compares not to a typical El Nino year, but to any year, to all years averaged out. We would have expected in this particular El Nino to have maybe 200% of normal precipitation. But as you can see, in the Pacific Northwest, they got about 150%. In Northern California, it's pretty close to 100%. Boy, it was noticeably better. But in Southern California, it was sometimes only 50% of normal, even though it was an El Nino. And the cause for that turns out to have been unusual persistence of high pressure off the California coast, pushing the moisture northward and keeping it from California. And we had in the really serious drought years, we had what was called the ridiculously resilient ridge of high pressure out there, which really dried us out. This year it wasn't so ridiculously resilient, but it was still there. And the question is this now the kind of feature we're going to have to live with for a long time in the future? And we don't know. A key point, though, is that it's driven by CO2 for the most part. And my recipe would be to outlaw coal, which is certainly the largest contributor to greenhouse gas warming. I even see fracking as a potentially good step if it results in more production of natural gas, which can help us step away from coal. Mostly, I think I have to agree with Barack Obama, who made this summary. Climate change is a potential existential threat. It's a political problem perfectly designed to repel government intervention. It involves every single country, not a good idea. It's comparatively slow-moving emergency, so there is always something seemingly more urgent on the agenda. And we have to somehow collectively learn how to deal with that unprecedented circumstance and to work around it however we can. But let me stop there and answer any questions and hear any discussion. Yeah?
Could you restate questions or ask someone to come up to the mic so people who are listening to the video can hear?
What? I got an idea.
John, there's a microphone, a hand microphone in that stand right there.
Oh, but I'm going to stand there, and people asking questions can pass this one around.
John, I've read some articles in the chemical engineering literature that do some calculations of the reduction in CO2 that would occur if coal-fired plants were changed over to methane, which produces less than half the CO2 emissions. And some of those calculations, the authors indicate that the balance could actually be reduced. The overall cycle of CO2 includes absorption of CO2 by plants and other things and transfer to oxygen. That cycle, the increase could actually be reduced if methane were the fuel. And I was just wondering what you think about that.
I think it's true. I think that the use of methane as a power generating source is potentially very beneficial, especially because methane-fired plants can be engineered for quick startup and shutdown, so that they could be used to fill the gaps that you get inevitably when you have solar power and stuff like that. So the danger is, or the point would be, it's still a fossil fuel. It would be better to not have to use methane, but methane is so much better than coal. Coal is less energy per mole of CO2 you put into the atmosphere, and coal plants are practically impossible to start up quickly and shut down quickly. So as long as you stay with coal, you're condemning yourself to persistent and high emissions. So stepping away from coal is the single most important thing I can see we could do. Yeah.
Here comes the microphone.
Sorry, here comes the mic.
Would, in place of methane, would nuclear be a better solution?
Nuclear is not a fossil fuel, and apart from the dangers of managing it, it's preferable even to methane. The difficulties are it's a fissile material, and it has associated political and military hazards. If we could manage those perfectly, it would without a doubt be better even than methane. Fission power.
I just have a brief addition to that, which is that there's a huge problem with disposal of spent nuclear rods. Nobody knows what to do with them. And it's just a huge, the more of those you make, it just increases another really big problem.
I don't think the nuclear waste problem is scientifically insoluble. I think it's politically practically insoluble. Believe it or not, I'm an oceanographer by my dearest scientific associations. If we put nuclear wastes into clays that were descending into subduction zones, I think we would never hear from them again. But people are so horrified by the possibility of using the ocean as a dumping ground for nuclear waste that it has proven always to be a non-starter. And in fact, I think it's the best single idea that I've heard. It's not cheap, it's not easy, but it's more possible and potentially much safer than any of the other. I can explain it in brutal ion exchanging detail if you want to know, but it's a good possibility.
When you explain it as clearly as you have, at least from I'm somewhat of a scientific background, I find the arguments quite easy to understand, and yet politically speaking, getting the public to accept climate change has been difficult, to say the least. It's up there with evolution. And yet, here there will be a meeting of all the Republicans in Cleveland, and I'll bet this will come up as if this doesn't exist. And so there are large economic reasons for why they don't want to believe it to be true. But I think there's also a lack of complete understanding about the scientific principles that underlie these problems. So can you expand maybe on what can we do to make this better? Is there an age belief difference as well between young people and what they're learning in school and older people? Are we getting any better in terms of education?
As a psychologist, I make a good geochemist. I honestly, what I was saying today illustrates part of my belief, and that is that if we could get people really to understand how utterly compelling and how fundamentally inescapable the basic physics of it are, that it would change things fundamentally. I think that people who have an understanding, but a shallow understanding, of greenhouse warming, and who abhor so-called climate deniers, we need more of those, but I think we need, in particular, all kinds of people to understand the real nuts and bolts, so that they understand how this is not, the idea that there's a debate about it is just breathtaking. As long as there's, any idea that it's debatable, then it's a license for economic greed to play a major role in shifting opinion. And so the key to it, it seems to me, is to clarify as insistently and patiently and carefully as we can the sort of absolutely fundamental security of our understanding of greenhouse warming or greenhouse effects on climate change. Yeah, Ron.
Hey, I may have missed something, but the high pressure ridge off the coast, do we know how that's related to warming or CO2? The fact that it's there and not somewhere else.
Yeah, this is the classic question of, is it really related necessarily to greenhouse effects? And the answer, I think, can now be probably, more probably than not, but there's no certainty. The fact that we know that all this energy is being retained, and we see there are scholarly studies, for example, of Atlantic hurricanes, demonstrating statistical significance rigorously in the power being released by Atlantic hurricanes, and a correlation between that and sea surface temperatures, and the sea surface temperatures clearly being driven by greenhouse warming. I know of no such analysis for weather systems in the Pacific. And I was pointing to it as being consistent with, rather than compelling evidence of, the effects of greenhouse warming. It is the kind of effect you would expect from messing with atmospheric circulation. But there is no chain of evidence that has been articulated. There's this marvelous grad student whose name I've forgotten at Stanford, who has made himself into a commentator on this whole issue. And I'm just echoing him when I say that it's more probable and that it's something we can point to as a likely effect, but not a certain one. Jerry. Question is, what's the potential for solar and wind to help out? And I think the potential is terrific. They keep the rate of growth of these unconventional non-fossil fuel related energy sources. Each year it beats the prediction, and so I think that there's a very good chance. The difficulties that we have are a transportation infrastructure built on fossil fuels, and it's going to take decades to get away from use of gasoline and diesel fuel to drive transportation. That's just a huge problem, and solar and wind are not going to help us quickly with that problem. But they obviously are the sources to which we have to transition over time. Yeah.
If the burning of fossil fuels were stopped today around the world, how long would it take to change the atmosphere and the greenhouse effect?
A CO2 molecule that gets into the atmosphere stays there for about 5,000 years. So the E-folding time for the decline is long. But, you know, the moment you stop, you begin to see improved effects. Obviously, the most we can hope for is to just slow down the rate at which we're doing this. And that the fact that we're exceeding the normal flow of carbon from organic material to atmospheric CO2, we're exceeding it by a factor of 300, shows us how much scope for improvement there is and how much improvement is needed. There are people who you know, they say, well, we're already locked in to various effects, and the reason they say we're already locked into various levels of warming is exactly this problem with the fact that if we stopped immediately, the CO2 would still be there and it would stay there for a long time. The graph I showed with the forcing is from a paper by Hansen and about 20 other carbon cycle specialists dealing with what should we be shooting for? What level of CO2 in the atmosphere could be regarded as long-term safe? And their answer at that time was 335 parts per million. Now Hansen has chiseled himself up. He'll say, oh, maybe 350. But we're already well above that. Yeah.
I'm not a person, but I do have a question about the effect of global warming or climate change on animals in the ocean, animals and plants in the ocean. Are any species disappearing, or exactly what's going on in that?
Well, the biggest effect in the ocean at the moment is, seems to be biggest effect in the ocean at the moment is not so much temperature. There are larval forms of some shellfish that are being killed off by rises of temperature in some parts of the ocean. That's happening. But the most worrisome effects are those affecting organisms that can't move. Corals are being one particular problem. And there you have two things going on at once. You have acidification and from the CO2 in the atmosphere going into the ocean, making the ocean waters more acidic and tending actually to dissolve the coral. And you have the fact that the organisms, in particular the algae living within the corals, tend to get out of the way, or literally to leave the corals when the temperature gets too warm. So you get bleaching events which are caused by increases in temperature, and you get dissolution caused by acidity. The strange thing about the acidity problem is that there have been times in the past when we had even higher amounts of CO2 in the atmosphere, and yet there were corals everywhere. And so the question is, how does that happen? And the answer to that is that in those earlier times, levels of CO2 rose so slowly that the acidity was constantly neutralized by erosion of basic materials from the continents into the seawater, so that the alkalinity balance was not disturbed. Now what's happening is we're putting CO2 up so fast that the titration mechanism on the continents can't react rapidly enough, and we're acidifying the ocean. So that's why that's a problem. It's the rate that's the problem there. So, you know, it's another reason. It's different from warming, but it's another reason we should worry about CO2 in particular. Yeah, David.
John, I wonder if you can help clarify this. It's an intuition that I've developed from somebody who hasn't taken chemistry since 1969. So that's a long time ago. But the problem is, and our contribution to it, if you burn gasoline in a carbon molecule is not that heavy, but when you combust it, it combines with 2 oxygen molecules which are much heavier. So the weight of the carbon from burning a gallon of gas is going to be much greater than the weight of the gallon of gas. Can you clarify that for me? Does that make sense?
No. I don't understand the question.
So I don't know what the weight of a gallon of gas is, but I think the weight of the carbon dioxide you put into the atmosphere from burning a gallon of gas is many times the weight of the gasoline itself. Is that true?
David's asking a question that's basically about units. People talk about tons of CO2, and they talk about tons of fossil fuel. A carbon atom weighs the same, whether it's a carbon atom in fossil fuel or a carbon atom in CO2. In fossil fuels, carbon is bound to hydrogen or to another carbon. And each hydrogen has an atomic mass of 1. In CO2, carbon is bound to oxygen, which is 16 times heavier than hydrogen. So if you use as your unit of comparison tons of CO2, counting the carbon and the oxygen, and compare it to tons of gasoline, then the CO2 weighs a lot more than the gasoline because oxygen is so much heavier than hydrogen. But that's irrelevant. The real point is the carbon. And so that's why I use these units that might curl people's hair. I use moles of carbon, because that's what matters, is the moles of carbon, not the tons of CO2 or the tons of fossil fuel. And the reason for the weight discrepancy, which is, you're correct, but the reason for the weight discrepancy is just that oxygen is heavier than hydrogen. That's it. Sally.
I have a really simple question. When you fly, do you buy carbon offsets?
No.
Do
Do I buy carbon offsets?
Should we?
I don't know. I don't know about the offset business. I don't know whether it's being manipulated or whether it's really well run. The principle is a good one. Yeah, the principle of carbon offsets is sound. And the question is, are they actually being well run? I don't know. If they were being well run, then I would feel guilty by not buying them. So I protect myself by maintaining my ignorance. You guys are fantastic.